and Mechanical Engineering Club. I would like to start by welcoming you all to our seminar today. The title of today is Pump and Pumping System. The seminar will cover the main types of pumps, centrifugal pumps, principle of operation and its major components, the principle of cavitation, and pumps performance. And we would like today to welcome Mr. Lu'ay Faiz, who will present our subject today. Mr. Lu'ay Faiz is certified professional engineer by the Saudi Council of Engineers. Mr. Lu'ay has more than 25 years experience with Saudi Aramco, with different facilities, but mainly with consulting service department, rotating equipment. He is holding master degree of design in rotating machines from Cranfield University in United Kingdom, and bachelor in mechanical engineering from KVBM. He is holding ISO certificate for vibration analysis. Mr. Lu'ay is an active ASME member, and he presented various technical papers and case studies at several national and international conferences and recognized technical journals. Welcome, Mr. Lu'ay.
Assalamu alaikum. Good evening, everyone. It's my pleasure to be here today after this long time of being an ex, I would say, or graduated student from this great university. It's 25 years, it's a long time. It's really a pleasure to share with you some of the experience we have in pumps. So the presentation topic will be about pumps and pumping system. Before we start, I usually like to have the presentation interactive. If you have any question, you can stop me at any time and ask your question. Okay? And sometimes as well, I like to ask you questions, so just to see your interest in the subject. Pumps, are widely used in the industry. We consider them as the heart of the process. They are the fluid mover for the different process in different facilities and different industries. They consume in terms of cost, in terms of energy consumption. They contribute in a high percentage of power consumption in the facility, as well the cost of the construction in the plant during the plant design. So that means we should have a proper attention during the design, during the operation, during the selection of this equipment to make sure that we are maximizing their operation without sacrificing with the efficiency and the energy consumed in the plant. The objective from this presentation is just to give you an overview about the principle of operation of the equipment. It will contain the pumping classification, centrifugal pump principle of operation, centrifugal pump major component, pump shaft loads and pump performance, and pump cavitation and operate. We will go through some safety tips related to this the subject. I will try to avoid going in theories. Just I think you have it already given in the university. Now let me ask you, what is the function of pumps? Can someone tell me? Yeah?
Increase the pressure.
Increase the pressure. Is there any other function?
Transfer.
Move the fluid. Transfer the fluid. Yeah. We can say it's a mechanical equipment or device that convert mechanical power into hydraulic power. We have a motor or a driver, say turbine, gas turbine, motor, connected to the pump By rotating the shaft, you are just increasing the pressure of the liquid. You know, adding energy to the liquid in terms of pressure. We'll go through it as well later. As you mentioned, transfer liquid from point to another point and increase the fluid pressure. Okay? We will be we will be focusing more. We have two different, main classification of pumps. The first classification or type is what we call a dynamic type, and the positive displacement. Those main classifications are related to the way the energy added to the liquid. If we are adding the energy to the liquid continuously, that's mean we call it dynamic. If we are adding it periodically, we call it positive. Example of this is for centrifugal pumps. Whenever you are spinning the impeller of the pump, you are continuously adding the energy to the liquid. That will be turned to pressure, I would say, and it's continuously added. So we call it dynamic type. On the other hand, when we look at the piston pump, okay, piston pump has two stroke, suction stroke and discharge stroke. Whenever the piston moves to the right, basically you introduce the liquid from the suction valve, okay, to the cylinder, and by doing this you are not adding energy to the liquid. During the discharge stroke, you are compressing the liquid, you are pushing the liquid through the discharge valve, and adding energy to the liquid. So this is why it's considered periodical, positive, displacement type of pumps, because energy is not added continuously to the liquid. Okay. There are other sub-classification when we look at there are so many types of pumps and depending on the application. The main is under the dynamic. We have the centrifugal pumps. They are the mostly used type of pumps in the industry. Especially in oil and gas, we look for more than 80% of the pumps as centrifugal pumps, while the positive displacement are mainly used whenever you are not able to meet the process with the centrifugal type. Okay, so the majority of our, for example, in Aramco, when we talk about Aramco, majority of our equipment are centrifugal. They are more reliable. Even from maintenance point of view, they are better from maintenance point of view than positive displacement. So designers mostly use centrifugal pumps when they select, if they have the option to select. However, there are some challenging applications that centrifugal pumps cannot handle. If we are talking about a viscous liquid, okay, centrifugal pumps might not be a good option. Like heavy oil, for example, heavy stuff like viscous, like asphalt, for example. Okay, sometimes you cannot go with the centrifugal pump. Either you need to heat up the liquid to make it, with less viscosity to be able to pump it with centrifugal, which, depending on the process, you might not be able to do it. Or if you want to, do it with the lower temperature, you have to go with positive displacement pump. In this presentation, I will be focusing only on centrifugal pumps, because they are the, as I said, mostly used. Under positive, we have reciprocating pumps. Under it, we have diaphragm, piston, and plunger. We have rotary. Under rotary, we have a screw, vane, loop, gear pump, and rotary plunger. Okay? So, centrifugal pump. Let us talk about the principle of operation of centrifugal pumps. This is a side view of centrifugal pump. We have the suction flange, discharge flange. Okay? Whenever you spin the impeller, okay, You are basically sucking the liquid, introduce it to the suction flange, to what we call here impeller eye. It will spin through the veins to the discharge area, or this area what we call fluid. Okay? And it will be pushed to the discharge flange. Okay. How can we get the pressure? It's basically by introducing the liquid inside the impeller and spinning the liquid, we are increasing the speed of the liquid until it reaches the maximum near to the impeller tip. We call this area as impeller tip. Okay? So the maximum speed or velocity will be near to the tip of the impeller. Okay? What's going to happen after that when the liquid discharge, in your opinion? It's the whole thing is filled with liquid, but I'm saying, the speed that you get from the impellers, what's going to happen to it? Are you going to able to speed up more the liquid when you reach to this area? So, to convert to pressure. Okay. So the pressure will increase here, and by restricting the area, you are increasing it as well to reach the maximum near to the discharge flange. So velocity head is converted to pressure head. This is what's happened. If we consider this as the suction flange and this is the discharge flange, by the time liquid gets through the suction flange, the velocity will increase until it reaches the maximum near to the impeller tip. Okay? Then the velocity will drop. Okay? You can see here the velocity here in this area is slightly higher than the suction. Okay? Just because of the change in geometry. Usually the discharge flange is smaller than the suction flange. So you have a little bit increase in velocity than the suction velocity. However, the pressure will increase to reach the maximum near to the discharge flange. Okay? So this is the basic principle of operation for centrifugal pump. Right? Okay? Let us talk about the classification of equipment. There are many ways of classifying pumps. We can classify them according to their function of operation. As if we say injection pump, shipper pump, booster pump, or we can call them according to their, the media that they are, pumping, like seawater injection, crude shipper pumps, NGL shipper pumps, but the known and the industrial classification according to their design. Okay, we can classify them according to the way the rotor assembly. When we say rotor assembly, the shaft and the impellers. I'm going to go through the component later, but the shaft and the impellers, if they are mounted horizontally, we call them horizontal pump. If it's vertical, we call it vertical pump. Okay, that's one way to classify them. Single or multi-stage. If we have a one impeller, we call it single stage impeller. Okay, or pump. If it's multi-stage, we call it multi-stage. Okay. Theoretically, can we have only single stage to meet the requirement? Or let me ask you a question, why we go to multi-stage?
Maybe you want to.
Increase the head, but can we meet it with only single stage?
That's why maybe you need more. The differential pressure is high. A single stage cannot sustain.
Well, but we are talking about theoretically. What do you need? I mean, if you look back to the the cross section of the equipment, we are saying, the velocity increase, which determines how much pressure you want. So the larger diameter of the impeller, the larger pressure you can get. Okay, so that might theoretically means I can go with any size I want. What's the problem with going with this?
Not practical. Size limitation.
Okay, we're talking about theoretically now. Is it possible?
Yeah, I think no. Terminal velocity or something like that.
Well, let us say somehow it's possible. Okay, I'm not talking about like a very huge, I would say, or large pressure, but relatively, I would say, medium, I would say, pressure. You can go with large impeller diameter instead of going with multi-stage. However, you will be end up with a larger impeller, larger shaft to support it, larger equipment. From reliability point of view, it will be very bad. Okay, so it will be more headache, more capital cost on it, and less, in terms of reliability, it's going to be worse in reliability. Do we, as end user, interfere with the number of stages? No. It's a design preference for any vendor to select how many stages, how many you want to go. However, we have some limitation. For example, we say, the power handled by each impeller should not exceed a certain value. Why? Because if we exceed it, the loads on the impellers might cause problems, and we had problems. We learned from problems. Sometimes we add requirement in our specification just because we get it, problems that might not be even covered in international standards. So again, single or multi-stage, and it depends on the vendor selection. Single or double suction impeller, and this is to do with the if you remember the impeller, the suction eye. Is it from one side or two sides? It has nothing to do with how many suction flange. This is to the impeller itself. Is it one or from both sides? I will show you slides later to explain it more. Single or double. Overhang or between bearing, and this is to do with the way the impeller are mounted with respect to the bearing. If the impellers are mounted between the bearings, we call it between bearing pumps. If it's cantilevered, we call it overhang. Again, I'm going to show slides to explain it more. Radial or axial split casing, and this is to do with the split line of the casing. We might have a top part and a bottom part, a split line between them. If it's parallel to the shaft, we call it axial split. If it's perpendicular to the shaft, we call it radial split. Okay? Any question before we go to the coming slides? Okay? So this is example of simple overhang pump, where we have here the suction flange, discharge flange, and here we have the impeller. I'm going to go through the component in later section, but this is what we have. It's considered horizontal because the impeller and rotor mounted horizontally, it's not vertical. It's a single stage because we have only one impeller, so it's a single stage. We have a single suction because we have only one impeller eye, which is this area here. The liquid will be introduced to this area, pumped through the impeller. If we have another, a suction side for the impeller, we call it double suction. So this is a single suction. Overhang, because you see here, we have the bearings here, and we have the impeller here. So the impeller is overhang, with respect to the bearing. So we call it overhang type. Okay? And radial split, the split line is, when you look at the casing, we have this piece of the casing, and you see the bolts all around. If you want to dismantle the equipment, you just open these bolts all around and pull it out. So the casing split line, here we have a piece of the casing, and the other piece is this, the front side, and the split line is vertical, which is perpendicular to the shaft. So this is why we call it radial. Okay? Yeah.
Can you point out what is the split line?
Yes. عندنا هنا these are the bolts. طبعا all around. You can see it here. One here, وعندك others. Okay? When you try to maintain the equipment, you basically unbolt these bolts and then open it like this. So عندك here one piece and the other piece is here. The split line is like this. Okay? Yeah. Embedded? That's a good question, but it's good.
زي الشافت يعني why would you call a shaft a shaft?
Well, I haven't think of it, but it's a name, يعني.
Roll.
Well, I need to Google it. I mean, this is something I haven't think of.
It's just
Yeah, it's a name. Okay. Here is another like a complicated one, which is, you know, you have how many stages you think you have here?
six.
How many impeders?
6.
Yeah, it's a 6. Here, 1, 2, 3, 1, 2, 3. Okay? When you look at, you know, the impeller, look at the impeller eye. You know, where the liquid get introduced to the, you know, to the impeller itself. Okay? You can see here, this is the suction flange, liquid introduced in this area to here. Okay, then it will be pushed, طبعا it will be introduced to the impeller all around, يعني through the impeller eye. Then pushed through this cavity to here, second impeller, then third, okay, then it will be pushed through a cavity to here, then here, then here. Then it will be collected to the discharge.
ليش ما كملت طيب؟ Why
This is my question. I should ask you this
This
question.
يعني it doesn't make sense يعني. Why would it go that way?
Yeah, it does.
The thrust forces.
Yes. Axial loading. To balance the axial loading. And whenever you, يعني we will go through loading later on. Whenever you run liquid through impellers, you are just pushing the liquid. You are pushing the liquid.
Yes.
That
yes.
will push an impeller. So if you have them stacked in one direction, bearing, thrust bearing will be sized, يعني you will be end up with a big size of bearing to balance the radial load, axial load. So this is one way to balance the load by having an opposite direction impedance. So this is a horizontal multi-stage between bearing. You can see the bearing here. This is a bearing, and this is the other set of bearing. So and the impedance between. So we call it between bearing. Okay. Axial split. You can see the lower part of the casing, and there is a top part. The split line is this between the two parts, and it is parallel to the shaft. So we call it axial split. Okay. This is maybe clearer to show the split line. This is the bottom, and this is the top, and this is the shaft. So this is the split line. What we call split line is the line for between the two casing halves. This is the split line. Okay, so that's the split. All right. How many stages we have here?
5.
5. So it's 5. 1, 2, 3, 4, 5. Suction is this. It will be introduced to here. Second, third, fourth, fifth. Okay, so this is radius. Oh, radial because it's written radial. Okay, and you can see. I mean, why it's radial? Because we, this is like a special. Oh, well, I'm not saying special because it's special from the bad side. Ring joints, but the casing itself, when you have bolt all around, you unbolt, and then the split line for the casing is, vertical or perpendicular to the shaft, so it's a radial. It's a between bearing because we have a bearing here and here, and here, and we have impellers between, so it's a between bearing, radial between bearing. What else? Horizontal, yes, horizontal, tail split, okay. Multi-stage, okay. So, now you are ready to answer. What is this? Is it single section or double section?
Double section.
Double section, you see why it's
Yes.
double section. Okay.
Single stage.
Single stage,
Vertical.
Vertical.
vertical, okay. Huh?
لا ما عليك بالصورة بس.
It's a vertical, but we have another name for it. You know, vertical, and then when we reach to talk about the vertical, we don't call it overhang because without saying they are suspended. But this is vertical. We call it vertical inline. Okay, single stage, double section. Okay, radial split casing. All right, double section because you see the impeller here. Liquid is introduced from this side, from this impeller eye and this impeller eye, and then it will be pushed through this cavity or followed to the discharge. Okay, so it's a double section. Why do you think we have a double section? Is it because we love to have it like this? Huh? Well, what cost? Okay, so you can have impeller with one suction that will handle the same fluoride. There is
the forces.
Hmm?
Equalize the forces.
It's one reason, but it's not the main reason. Element? No, it's not. The same answer, but it's not the main. It do this function, but it's not the main.
Maybe for the street light, lighting.
Yes, but it okay, I will answer it. For any impeller, there is what we call it net positive suction head requirement, which is basically, let us say it, suction pressure requirement. Okay, and it's linked to the flow rate. The friction will play a big factor in it. If we have a higher flow rate, the suction requirement will be higher. Okay, if we split the flow as if you are splitting each side of the flow to each, I would say, can have separate impellers خلينا نقول, it will improve the NBSH requirement. I will go through cavitation later. But it's basically to improve suction requirement. Pressure requirement في عندنا available pressure في السيستم و required pressure by design. Okay. If we have a very low pressure, we might not be able to select equipment with a single suction. So we go for double suction to reduce the flow rate على كل side, which will satisfy the requirement حقنا. Okay?
So basically, decrease the MPS job for the one that
لا,
is coming
it's-
from the manufacturer.
لا, it's to improve the requirement. يعني خلينا نقول إذا جيت أنت حطيت if you split the liquid flow rate, ال NBSHR requirement بتكون أقل. That will mean أنك your available low value will satisfy the requirement حقكم. And you have to maintain a pressure or NBSH requirement available higher than the requirement. We'll talk about it probably the gene of cavitation more. Okay? What is this here? Vertical. How many stages? Or is it a single stage? How many stages do we have?
5 stages.
1, 2, 3, 4, 5. Okay. Vertical. Between bearing ولا لا. وما نقول overhang طبعا because suspended, because the whole thing is Radial or axial?
Radial.
Radial. And they are always come radial. You cannot have metal casing split like this. It's always عندك bolts هنا. Unbolt every piece هنا اللي bolts or bolts every one and the columns برضه. So liquid go from here, suction, first emperor, second emperor, third emperor, fifth, then go all the way to here. Why do we need the vertical pumps?
Depend on the application.
What do you mean?
Maybe it's a restriction or how to fit a regular pump.
Let's explain it more. يعني you cannot use horizontal.
Maybe depend on the, I don't know.
هو في سبب.
Take, for example, the oils underground, it's better to put one that can reach.
Yes. لأنها تكون هذه في صمب. عندك صمب or tank that will sump from it. But can't we use horizontal pump نوصلها لتحت؟ It's going to be a negative pressure that will not be. You see, one of the common problems that we have, if you have like in your home underground tank, okay? When you take an equipment off the surface for maintenance, bring it back, you run it, it will not start because it cannot suck from down. What do you do usually? Fill it with water. You prime it. You fill it with water, so it will create vacuum to burn.
طيب هل راح يعني تتاثر لو شغلتها وهي مثلا بدون مويه؟
شوف it depends. It will try to extract the liquid, so it's exerting force to يعني create a vacuum to burn. You might be end up with failing equipment because it runs dry, يعني it will overheat. إذا أنت if you are lucky you will level يعني not that far, it will struggle a little bit, then it will start to bubble. But it's for the long run, you will damage your equipment. So you have to fill it with water to cool it, plus to help it to create a vacuum. Sugar liquid. Good. So it's a vertical, suspended, multi-stage, single suction because it's a one location. Okay. طبعا هذه in the industry we have يعني معلقات من ناحية إنه okay the bearings for these pumps عندنا top bearings طيب they come like anti-friction bearings. Sometimes you don't see them في الpump, you see them في motor. And we have sleeve bearings like this one here. Okay, sleeve bearings. These sleeve bearings, you can see that they lubricated or cooled by the surface. All right, so it's a surface lubricated. Depend on the application. If you can use it to cool the bearings, يعني you can have it like this, or you might need to use external source to lubricate the bearings هذه. And from the industry, you know, end users had so many problems حتى في Aramco with operating vertical pumps when they get dry. These bearings they act as ignition source. If you have a flammable surface, for some, it might end up with a disaster. يعني not only يعني the multiple end users they had problems because of this. Okay. Here we have a different type. How many stages? Two. So what is it? Vertical, radial, suspended. But what's different between it and the other one?
The inlet and the output on the exhaust pump.
Okay. Oh, see it.
Two sections.
No. Liquid is introduced to this barrel or can, okay, and then liquid pass through first, second, and then discharge.
طيب ليه ما ينزلون الفلنجة هذه تحت؟ يعني عشان ما يخلونه ياخذ المسافة هذه كلها. يعني what's the reason behind this design?
هذا اللي كنت بسأله. يعني
ما امشي يا جماعة.
you remember how we talked about the cavitation? How do you overcome a cavitation? You satisfy a requirement. How do you do this? You introduce more pressure to the system. Let us say, and the system is pumping from point A to B. طيب الليكويد pressure في عندك friction في اللاين. By the time it reach here, I need to boost it up to be able to reach to another destination. Okay, I'm a designer. I want to select equipment here. طيب, and I'm limited with this location. I cannot shift it to there. Okay. My primary option is to go with horizontal. Okay. Calculation توضح إنه I cannot make it with horizontal pump, right? Because it's not going to be satisfied with the requirement. The pressure is not sufficient to satisfy my requirement. One way to improve it is to give it more head, and this is what we do. By bringing the impeller from this level to lower level, you are giving it a static head. All right. So to improve the, the suction requirement. So this you see it in the pipelines. It doesn't. It's not in a sump. There is no sump here. The can here is acting as a sump to improve the suction requirement. Sometimes you see the pressure is high already, but because of the vapor pressure for some liquid, they come with a very high vapor pressure. And again, we are doing this to improve the margin and avoid having a cavitation. So that's basically why we go for, we call it can pump, okay? So there's a vertical, suspended, double casing or can, multi-stage, single suction, yes.
Why can't we do a multi-stage normal one? It will give more head.
You mean horizontal?
Yes.
والهوريزونتال اللي بسبب ال NBSH requirement will not be satisfied with you need higher suction pressure to be able to use the horizontal pump. عندك two options, either to be able to construct something here or to bring it earlier. If you bring it and shift it earlier, then you are pumping from, let's say, Dhahran to Riyadh. You see, مثلا, we reached Abqaiq, okay, and we have a problem. If we can construct a facility before Abqaiq with a horizontal pump, that's fine. But sometimes you are limited. We cannot do anything here, so we have it here, and we end up with this. Okay.
So basically losing the elevation.
Yes, to provide more head. Yeah. You look at always the pump when you talk about NBSH, impeller, sorry, impeller. Am I satisfying the NBSH requirement for the impeller? طيب. في another type when we talk about the vertical pumps, what we call side discharge. In side discharge, we have the suction here and a side discharge column, right? And this is the what we call bore column. You have the column here. You have sometimes the bearing or bushings, and you have a bushing here. Okay? This bushing is lubricated from outside, either grease or liquid or even oil, lubricated from outside. But the most important, it's a side discharge. Why do you think we need it? Why we didn't go with the same option, discharge through the column? To save, instead of having two columns, we have one column. Is there a reason? No. It's a size. I can control the size. There is a reason. Okay? A reason sometimes I cannot pass a liquid through bushing. It will damage them. Okay, so you go with the side discharge. And البوشنج نفسها lubricated by other means. That's one يعني reason. عادة designers they or vendors they offer this because it's smaller عادة في السايز than the discharge through the column. But there are limitations for this. We usually use it في common sewage application, chemical application, and for molten silver application. Molten silver, if it's passing through bearings, it will damage. It will damage the bearing. Sewage, the same. We don't use discharge through the column for sewage or chemical, purple. However, سواء Aramco or other oil companies, they got to use these types يعني for many years. Okay, in oily water, in hydrocarbon application, until they started to have problems. These bearings, just imagine during the like their because they depend on their lubrication from outside. If you don't keep a good maintenance on these bearings, on lubrication, you might be running them dry. And if you are having a flammable hydrocarbon application, an explosion might happen. And it happened. You can Google it. So many incidents, some of them with fatality, happened in different places in the world because of this type of equipment. Okay, not because the type is not like the right thing mainly. It's because of the way we maintain it. Okay, so now the majority of the end user in oil and gas, they don't use it in flammable hydrocarbon application. Okay. Now let's talk about the major component of pumps. We have the casing, the shaft, impeller, wiring, mechanical seal, and the flanges, bearing, and the drainage. Okay. So if we back to our pump here, we have the main, the shaft, and the impeller. Impeller is the main or the most important part to play it defines the hydraulic of the equipment. Okay, the design of the impeller will define the requirement of the that you want. Okay, it's supported by the shaft, and the shaft is supported by the bearing. We call the bearing closer to the motor drive end bearing, and the one to the other side, we call it non-drive end bearing. We have the mechanical seal here, and the function of mechanical seal is to prevent leakage to atmosphere. Okay, for safety, for operation losses, for environmental reasons as well. Okay, so this is like an element that will restrict the flow from going outside. Okay. One thing maybe, because we will discuss it later, we have the liquid here pass through the impeller, so you have here a suction pressure, and here you will have a discharge pressure. And this area in the back of the impeller and the front of the impeller, you have what? Suction or discharge?
Discharge.
Discharge pressure. Okay, so just to keep in mind, because we will talk about it later. We have here impeller wear rings. I will show it in other slides. And what else? Casing. Yeah, that's I think all. Yeah, here is the more casing, impeller, shaft, bearing, and we call this bearing housing. And here you see two rings, wear rings. One called impeller wear ring, which is attached to the impeller, and since the impeller is rotating, it's rotated with the impeller. And a casing wear ring, which is attached to the casing. Okay? Why do you think we need them?
Easier to maintain.
أعطيها direct كده
To control the wear.
to control the wear. Yes, yes. So it's easier to replace, because the other option is to have a tight clearance between the impeller and casing, and whenever there is a damage, it's a tough luck. You have to replace the bearing or repair the casing, and it's going to be like an extensive repair. Is there any other reason for it to have them?
Axial host.
لا.
For metric efficiency of the pumps.
Yeah, give me more details and straight to the point.
Prevent the recirculation.
Because imagine if you don't have it, what's going to happen? The liquid will circulate back to the suction. And what's going to happen?
Less efficiency.
Well, this, I would say the performance will be lower to the equipment because you have a circulation. So that's another reason for having the wear rings clearances are very narrow clearances. And they have to be selected right from material point of view because you just have two rings, they will expand with the heat. Okay? So you don't want them to end up with touch. Like, expansion, the casing wear ring is holding from outside. Yes, I mean, with the heat, the whole thing will be expanded, but it's limited by the casing. Where the umbilical wear ring have more freedom to expand. Okay, so you might be end up when you select a bad combination for the material with our suspension and seizure. For luck, we call it seizure. So it has to be selected right. Again, just to show the importance of it. If we are talking about an application that has suspended solid, this suspended solid will erode the area and open the clearances. Okay, and by the time you discover this, you might be losing a lot of energy in terms of the pressure drops. Okay, and imagine like in water injection application, when we talk about our big pumps, we are talking about 20,000 horsepower plus, just a little clearances opening means a lot of losses of millions a year in terms of energy losses. So it's very important to monitor the performance of the equipment to fix any problems. We have the one in front, we call it front wear ring, and the one in the back, we call it back wear ring. Okay, there is another function for it as well. When we talk about the axial loading, here we have, I'm gonna go through it maybe later as well, but here we have a discharge pressure, but with a smaller area, and here suction pressure. If I want to control somehow the pressure distribution, I can maybe, for example, shift this one to be here. So the discharge pressure in this area will gonna be only limited to the top, for example. So it's another way to balance the axial loading. Okay? I want you just to see this area, this thing here, which is like a wall extended inside the casing of the volute. Okay? We call it double volute. I'm gonna show it later. It has a function. It has a function in balancing the radial load. But this is just to show it here. Okay, this is another, it's a similar, but I want to show you only here two things. Here we have the bearings. The bearings, they don't come submerged with oil. Okay, the anti-friction bearing, you don't submerge them with oil. You just have a liquid level, oil level to rarely what we call the outer race of the bearing. While you have an oil rings that will pick up the oil and splash it to lubricate the bearings. These are, they are, like an oil ring or deflector just to pick up the oil and splash it. Some of the bad habits we have in operation facilities. Whenever they see high bearing temperature or an indication of oil problem, they think it's because of the oil level. So they fill it with more, and if you fill it with more, basically you submerge the bearings and it cause more problems. Okay. Here we have, when we talk about the sealing, we have here an alternative things which is we call it packing. It's like a rope. And it's squeezed between a shaft sleeve, which is this one, and the casing. It's act like a mechanical seal instead of a mechanical seal. The bad thing about it, it has generate high friction. And this is why mainly it's not widely used and it's not allowed actually in some of the application. Because it's designed to leak. There should be some dripping to lubricate the, the bushings. The backing. We only use them for the fire water system. Do you know why? The difference between the backing and mechanical seal, when they fail, it's a tough luck. For fire water pump, while you are trying to fight the fire, failing seal means you lost that. While the backing can be tight, even if it's leaking, it's not gonna be excessively leaking like the mechanical seal. So, in general, they are mandated for fire water system to use the backing. Yeah. Shaft sleeve is like a sleeve attached to the shaft or in the top of the shaft. The backing had a squeeze between the sleeve and casing. You don't want to have a damage to the case shaft, so this is like sacrifice instead of the shaft. If there is any damage, I can replace this sleeve. Yeah, when you look at the bomb design, you have different sleeves in different positions, but they do the same function, which is wear instead of the shaft.
Sacrifices itself.
Yes. Okay, this is how does it look in reality. We have a pump, this is the suction pipe, discharge flange. This is the bearing housing, mechanical seal, and the line here is the flush line for the mechanical seal. Okay, and there are many sealing mechanism, flushing mechanism. We're not gonna go in details in it because it will require another night. We might be talking only about the seal itself as in the coming slides. Okay, this is a between bearing pump. You can see here how many stages we have here. I've had
5.
huh?
5. 6.
آخر كلام. 1, 2, 3, 4, 5, 6. This is the 6. Okay, this is the first actually. Suction it's a double suction envelope. Okay, so directed to here and here. So it's double suction. Then you have the 4 stages. Here, unlike the previous one, they are stacked in one direction. Okay, double suction you can tell because the pressure here is low. Okay, so they use the double section to improve the requirement. Okay, between bearings, we have the bearings here. What else? Suction, discharge, mechanical seal are here. And the shaft. الكابلنج يكون هنا وبعدين عندك الموتور. طبعا هذه البمب we call it barrel type because the insert here or the cartridge is considered a pump itself and the barrel is another casing. So whenever you want to maintain it, you just pull the bundle. Okay, why do you think we need it like this? It's definitely more expensive, but is there any reason to go with this type?
Maybe it can handle higher pressures.
Higher pressure, yes. Or sometimes if you have a very sensitive surface with a light hydrocarbon that can easily leak. Axial split, they can easily leak, unlike the radial split. They can, they have a better option. The sealing here is the flange, the casing flange. Okay, so if it's gonna leak, it's gonna leak from the flange, which is right. Okay.
So it'd be correct to say the section, the double section is play a balancing thrust role as
No,
well?
no. So the main is to improve the requirement for the
Usage requirement.
In this case, it's not. But again, when we talk about the double section, you see here we have it only at the first stage. It's always at the first stage. You don't see it in the follow stages. Why? because we need to improve the low suction requirement. By the time that you discharge from the first stage, خلاص, you don't need it. So you only see a double suction for the first stage. You don't see it for the 4 stages. Okay? Here is an example for the impeller. This is the suction or the impeller eye. Okay? Here where we fit, in fact, this is there, the impeller, the wear ring. You see the wear ring? The impeller wear ring. It's locked with, screws, so they prevent its rotation. Okay? And if you have like high velocity, sometimes they get loose. Even the bolt might be shred with the high forces on them. Especially for large impeller. The liquid is introduced through the impeller eye. I believe this type is double suction, but it's not shown here. Double suction. You see it's introduced and pushed through the veins to the discharge. Okay? Here where, the wear rings, if we take this as the impeller, this is the casing, this is the casing wear ring, this is the impeller wear ring. This is how we secure them with the screw. This is stationary, and this one is rotating. Fluid pressure is here high. There will be some leakage to the suction, controlled leakage. Okay. If you have excessive leakage, there will be higher circulation. So it's important to keep keep them with within the tolerances. Not with a high. How can we check if we have a problem with the bearings without opening the equipment?
You can see the bubble increases, the volume. It's by the same.
Performance. If there is a drop in the performance, it will be seen as a drop in the performance curve, and that will give you indication. Either there is a damage in the impellers or an opening clearances. Damage when we talk about especially cavitation. Okay, here we have the wear rings. Okay, here and here. This is a double suction impeller. You can see the impeller liquid is introduced from the suction flange through this area and this area, and collected through the balloon to the discharge. And you have the wear rings and wear rings here. Okay. Mechanical seal. Mechanical seal is, equipment or device to prevent leakage to atmosphere for the reason we mentioned before. Okay. It has stationary component and rotating component. Stationary component, whatever bolted with the casing is considered stationary. It's not going to rotate. For example, the casing or the gland, we call it a gland for the seal, is attached to the casing. So you can imagine that this component is static, it's not rotating, stationary. Okay? While anything with the shaft or sit on the shaft will rotate with the shaft. So, for example, this sleeve is rotating because it's set on the shaft. This gland and this face of the seal, we call this is stationary face. Okay? And because it's sticked with the flange or the gland of the seal. So this is stationary. And this one is rotating with the sleeve. Okay? So it is rotating face and stationary face. Right? You have other component to seal because liquid will try to leak from different sources. It's either when you just imagine this is bolted to the casing, the first thing it will try to leak from between the gland and the pump, so through this O-ring. So this is a static component to seal liquid from going out, and it will try as well to leak from under the sleeve. So we have an O-ring here to avoid having it going through to the to atmosphere, and you have the other component like the primary component is the seal faces. Seal faces are maintained with a very narrow gap. The distance between the seal faces is thinner, like 1/60 of the human hair. Just imagine. And how do you maintain it? You have this, like pressed with a spring, and it's designed with, in a way that will, when you introduce the liquid, it will open. Okay? Opening it much means you have more leakage, because you have to lubricate. Okay, just imagine you are rubbing one rotating surface to another static surface. It will generate heat. You have to cool that surface with whatever liquid you are introducing. If you introduce more, that means leakage is more, which is not good. If you introduce less, there will be more heat, and the damage, it will end up with a damage in the mechanical set. So it's a control. During the design, there are different parameters need to be taken to make sure that opening is controlled in a good way. All right. So this is basically the mechanical seal. You have the liquid goes from the flush. This is the flush through the seal faces, and then it pass like this area to the drain line or of the seal. And there are different sealing mechanisms. This is the simplest. One single seal, no backup. There are different depending on the the application you have. The flush itself is like a different flushing mechanism depending on the surface and the top type of it. Okay. Bearings. طبعا bearings عندنا what do you think is going to rotate from this bearing? An inner race. An inner race is rotating with the shaft. The outer is is held by a bearing. So the type of bearing بيعتمد سواء roller, ball bearing, spherical, double, single. تعتمد على اللود. How much radial or axial load that bearing see. Some bearings they only handle radial, while others they handle radial and thrust. يعني تعتمد على هذا. This is the simplest يعني single row ball bearing. Okay. The impeller type, we have different impeller type. We can classify them according to their flow of direction. We can say we have radial, axial, mixed flow, or the impeller shape. We might have closed, open, or semi-open. Okay. A single or double section, like what we did in the flow. These are the main classification of impeller. Double section, because we have a double eyes from right and left. So, as you said, to improve the NDSH requirement. And axial, when the flow passes through the impeller axially. We're talking about the impeller, like the propeller of the ship. It's axial flow. We're not talking about the flow through the pump. We are talking about flow through the impeller, axial flow. Okay, you can tell the if we go to the first like a slide or first slide, when we talk about the diameter, that these type of impellers are not built to generate pressure. They are just to push flow. So they are producing a low pressure with for higher flow application. Okay, we have a mixed flow impeller where the liquid is not going radially like this one. It's just like a 90 degree, so we call it radial. This one, no, it goes with an angle. We call it mixed flow impeller. Okay, we might have an open impeller that where the we have the impellers. The impeller vanes are contained with what we call the shrouds here. Okay? All right? Sometimes we have one from one direction, we have two direction, we call it closed. Sometimes we have it only in one direction. So, or open. So it's from both sides. There is no like the axial flow. So it doesn't have shroud. So we call it open. Semi-open, closed from one side. Okay, like this one. Just from the back side it's closed. From the front side is open. Liquid goes in this way and pushed radially to the discharge because it's closed from one side. You can tell that you are looking somehow for a relatively medium pressure on this side, and let us leave it later. To the coming slide. Sometimes you have what we call it bump out veins, which are veins in the back side of the envelope. Okay. Do you know what's the function of them? Yes, it helps to balance the axial thrust because it's introduce a pressure on the other side. As well, it has another function, which is the main function. From their name, they call it bump out veins. Usually when you look at the impeller, liquid will try to go to the back side, and if you have like a suspended solid, it will accumulate in that side and damage the pump and the seal. So this is another option to go with what you call bump out veins, that it will push out any solids from accumulating in the back side of the impeller. So it's just bump out veins. Okay. We might closed impeller because it's the veins are contained within the shroud, so we call it closed. Sometimes we have a special type which we call the Francis type, twisted veins. You see the vein, if you trace it from here to here, just like a twisted with an angle from this to from here to here. We call it Francis type. You might ask, why do we need to, which one to select? As end user, we don't select. It's part of the design given by the manufacturer. There are certain, I would say, requirement that vendor, should go through to define which type that can be selected. We have a criteria called specific suction pressure. It's given by this formula, RPM, which is the rotation in RPM, times the square root of flow in GBM, gallon per minute, divided by the head, which is in feet. Okay? You can tell if you have high flow, what's going to happen? Is this number going to be high or low? High. This is high, this is low, relatively low, let us say. So the number will be high, we are going to the right, it's axial flow. Okay? Okay, what's going to happen if we have a very low flow rate, high head? It's going to go to right. We will end up with this type of equipment. That will be larger impeller diameter with a very narrow gap between the shrouds to give you very high pressure, low flow rate. Or we might sometimes fall in between. We mix the flow, Francis type. So this is what define what kind of impellers that you might need to select. And as end user, we don't get in this. It's design, the vendor to select the equipment based on like these requirements. Okay? Casing, can be radial or split, radial split or axis split, as we explained. Single volute, double volute, diffuser, staggered volute. These are related to the geometry, the internal geometry of the casing, and this is what we're gonna cover now. This is the axial. This axial split, top and bottom. Imagine when we talk about the leakage, like we have a light hydrocarbon. It's the area, the flange area between the top and bottom is very large, so the chances of leakage going to be very risky and high for axial split. This is why we don't use it for light hydrocarbon or high pressure application. Okay. This is how it look like in real picture. This is radial, axial split. This is the split line, top and bottom casing. Okay. This is the radial split. We have the split line here. This is the flange. So it's a radial split. Okay. This is a real picture for radial split. This is the split line here. Okay. Motor and gearbox. طيب. Now let's talk about the the load, pump loads. We need to understand the loads of the generated by the through the pump to be able to support it with the bearings. Okay, so we have radial loads and axial load. From where we get the radial load and axial load, we have static pressure, static forces like the weight of the shaft, the weight of the rotor, and we have a dynamic forces comes from the liquid flow itself. So these need to be understood in order to select the right bearing design or modify the the geometry of the pump to reduce the loading. Okay. When you look at the best efficiency point, where you have a smooth flow, the distribution of the forces on the shaft, if we take this as a shaft, طبعا الامpeller will be mounted on the shaft, but just let us imagine that this is the shaft. Okay. The pressure distribution or axial forces distribution through على الشافت will be almost يعني خلينا نقول the best in terms of distribution على the best efficiency point. It will not be eliminated for sure. There will be still some loaded, but it's going to be like a minimum. Okay. While if you operate away from the best efficiency, you will imagine there will be some turbulent, okay, which will lose the balance that you had. It's not a balance, but the condition that you had in the best efficiency. So you will be having more loads in one direction than if you operate على the best efficiency. It will be more and more. The more you go away from the best efficiency, the higher forces that you will get. احنا قاعد نتكلم عن الراديال لودنج الآن طبعا. Radial loading. So the radial loading force on the bearing radially from the shaft. Okay. بعض.
الحين non-distributed force شو بتسبب
forces على الشافت تعطيك vibration. Okay, التربلنت اللي جايه في البمب هذه كلها will be seen as a radial loads على الروتر that will be seen as a vibration because the whole rotor is not like running in a smooth condition. More vibration basically, more loading على البيرنج.
بس هذا ما exhausted ويروح البيرنجز.
يا بس انت الحين شوف تخيل انه مثلا عندك turbulent. What is gonna happen؟ انه بتكون عندك stability is not gonna be smooth. يعني بتكون عندك more movement على الشافت نفسه. It will be seen as a more vibration. More vibration will impact the reliability حق equipment. So this is not what you're looking for. يعني why we say انه مثلا avoid running away from the best efficiency.
I do agree we should run يعني nearest to the best efficiency point. لكن I'm after how severe.
It could be very severe to the point انك you damage the equipment very quick. يعني خاصة نتكلم عن high energy equipment, running them low flow for example, okay, very low flow rate, you can damage it within seconds.
Because of cavitation.
Because of cavitation, even when you look at very high, خلينا نقول مثلا حتى على because of vibration. Okay. احنا الاريا هذه احنا طبعا ولا نجيب هنا الاريا هذه we call it volute. If we يعني take يعني خلينا نقول result forces in it's acting as like in one direction and one to here مثلا. If we just imagine a liquid flow is going from between the veins all the way to here through the volute to the discharge flange. During a normal operation, the result there will be a force that will be act على الشافت. This is the shaft. It will be a force. Let's just imagine in the shaft, a force is acting this way. Okay, so it will be pushing it to this way. It might be يعني very high to the point that the equipment might not stand for. إذا تكلمنا عن overhang pump, for example. Let us say احنا عندنا مثلا في standard limitation for the size. Why? Because we know for a fact if we have it for large equipment with a very large load array, it will have a very high vibration that will not يعني gonna have a good or reliable equipment. So احنا for example طبعا Aramco or other end users they limit this like single volute to a certain size. Okay? إذا زاد عن السايز بيكون معناته إن اللودينج أكثر stability يعني بتكون not as good as if you have it with other option. فالother option إنه they have another wall they call it double volute. Double volute هذا what does it do? If you remember one of the pictures, it was showing the volute extended to the discharge flange. It's basically split the liquid flow from to this direction and this direction. طيب? So you can imagine in the liquid will exert a force to this way, طيب? And other the opposite. So it will somehow reduce the radial load على الشافت. And this is one way to balance radial loss and radial load and reduce it using a double volute. Okay, that's one of the simplest way. Okay, just imagine if we can have more walls vertical, that will improve as well more and more the radial loading. And this is what we have when we have a diffuser type. diffuser هذا يكون stationary element مثل هذه. طيب هذه stationary veins. طيب that يعني liquid passes through and split the liquid between the the veins, stationary veins, هذا impeller. So the liquid will be pushed through the diffuser veins and that will give a very perfect balance for the flow and end up with a very smooth balance for the radial load. ممكن تقولي why then we don't go with this? خلاص forget about it. Other options. Why do you think?
It doesn't work for any other one that vibrating noise.
Oh, in fact, this is perfect for a wide range. Yeah. No. Cost. We're dealing with cost. This is more expensive.
Only cost?
Yeah, it's only cost. This is cost. يعني هذا المين issue. طبعا في a between option for radial loading, what they call it staggered volute. And just imagine now, this is the first stage and this is the second stage. Okay? We said إنه axial load is acting this way, right? Here, for example, it's acting this way, and the other one is acting this way. You look at it, they are balancing each other, يعني somehow. يعني. So that will balance the radial load. Okay? That's another option, cheaper option. طبعا احنا مثلا كاند user, we don't say go with this. احنا نتكلم عن multi-stage. Sometimes they go for staggered volute arrangement, or sometimes they go with diffuser. It's vendor call. احنا بالنسبة لنا نبغى equipment with a certain efficiency. عندنا what we call it life cycle cost evaluation. Okay? This is the criteria how to buy equipment. How much it will cost us to operate it, to maintain it for 20 years. We count for energy consumption, which means that we count mainly على efficiency, power consumption, we count for maintenance and capital cost. Sometimes the capital cost is peanuts comparing to the total thing. So that will push him to go with diffuser if he is not able to maintain the efficiency. Yeah.
When you have it here, when you operate far from the best efficiency point.
تصبر لي شوية موجود السلايد. I know what you are looking for. But this is what we have as a diffuser. This is what you are talking about. This is the performance curve, okay, for centrifugal pump. If we take this as a best efficiency, loading for best efficiency, comparing the diffuser, single volute, and double volute, become for single volute very high, relatively higher than others, okay, than the diffuser or double volute. طيب, when you deviate and you have a wide operation range, you are operating with a wide operation range. شوف انت الحين الفرق بين اللودينج، هذا طبعا الكيرف حق الراديال لود، هنا بيكون lower with respect to this, but the increase is very high. شوف it jumped from here to here with a single volute. That's a proof argument earlier when we said it's not recommended for large equipment because basically we'll have very high loading and that's not going to be a good option. Okay? So this is the single volute. For double volute, there is a huge difference. You see the difference between them is very high. But still, there is a deviation, I would say, or increase, and when you go away from the best efficiency, it will increase the radial loading. The diffuser is the best. You see, deviation is little, so it's the best option in terms of loading.
So what about the hydraulic losses then? If you deviate from the best efficiency with the diffuser?
اللوسز يعني اوكي طبعا احنا بنتكلم عن مثلا اذا جينا تكلمنا عن efficiency, sometimes going with diffuser type will give you a best, I would say, or a good flow that will خلينا نقول improve your efficiency خلينا نقول. But if you compare it إلى best efficiency point حق equipment, sometimes على حسب الديزاين like turbulent losses due to turbulent في ال diffuser. Sometimes the efficiency that diffuser type have is lower than the diffuser type. But in general, احنا عادة we don't operate على best efficiency.
يعني close to it.
يعني بس بالغالب it's not very close to. طبعا احنا عندنا equipment either تكون standard or custom type. If it's custom type, we try to يعني operate يعني select it على very close to the best design, best clear to closer to the best efficiency, but there will be always يعني some gap. Yeah. Plus ان احنا في عندنا فرق بين ال design point and the normal flow. Normal flow اللي هي average flow through the year. So that will like an average flow, which means انه equipment will not be exactly operated على exactly على best efficiency. No, it with a range. Okay. Axial load عندنا forces on bearing from على axial يعني direction. When we look at يعني خلينا نقول from a static point of view, البريشر في على البومب عندك suction pressure على الامبلر عفوا suction pressure, and you have from both side discharge pressure على الامبلر. Yeah. both are discharge pressure. طبعا you can see the pressure here is higher. Pressure, since this discharge pressure and this discharge pressure, these will cancel each other. You will be left with this, and you can tell this is lower and this is higher. So you will be end up with pushing the impeller to the left. Okay, this is what comes in reality because you have some losses. So it's going to be like a pressure distribution. It's higher here, lower when it's reached to the bottom. But in general, this area and this area will see the same, so it will cancel. So you will be end up only with forces from this area. So it's acting in one direction. طبعا why we need to okay خلينا قبل نقولها هنا كده. طبعا في عندنا برضو other element على الاكسيال loading, especially when we talk about the vertical pump. اللود حق الشافت has to be counted. Sometimes you have to count. طبعا vertical pumps are very sensitive or bearing design very sensitive to the mode of operation. لأنه sometimes يكون عندك الفورس higher على one direction. Then if you change your operation condition, it might be pushed to another direction. So you have to design a thrust bearing for this variation للaxial loading. Okay, we call it active and non-active side. الactive اللي هو normal process thrust direction كانت active, وعندنا non-active اللي هي تكون abnormal then يعني like opposite تكون acting from another direction. Okay, let's talk about the head الآن عشان talk about the performance. The head can be defined by different things. Head is energy per unit mass, or head is elevation difference, or head is differential pressure when you convert the pressure to head. If you have a liquid is pumped from this level to this level, this is what you get as head, right? There is, whenever you look at the pump performance curve, you see it head versus flow. And the relation between the head and flow is head equal to differential pressure times 2.31 at a specific gravity. So whenever you change the specific gravity, the head خلينا نقول تكون ثابت for a given flow rate, it might impact the given or generated pressure. One of the things that we have to understand during the early stage of design, requirement for the pump. The designer, when he start to construct or design the facility, he starts with the static equipment. What is the requirement for a feed? Static equipment pressure like a vessel, a reactor, كم السورس اللي جاي لك flow, pressure. Then when he designed his network with the piping, everything, he go and select the equipment, the rotating equipment. So it comes at the last point. First you have to understand the system requirement. Okay, how much is required to push you from here to that point? How much resistance from the system gonna be seen, so I can overcome it with the good size equipment. Okay? This is something that you don't see in daily activities. It's just like unless you have a change in the design, but it's like a design stage. Yeah. So it determines head required to move the liquid from a point to a point, and you have 3 components to look at: static pressure difference, how much pressure here, how much pressure there, how much I need to boost up the pressure.
Static is
Static because it's a fixed value. Like pressure here is 100 psi, pressure there is 5 psi. I want to have like a 50 psi that will be pumping the liquid from here to. Elevation difference, how much, what is the liquid level in this point, and what is the liquid level. And they are static, static values. And there is a friction resistance. Friction resistance, is it static? It's not. Okay. When we say static, we basically look at it from, with the respect to the flow rate. I have a pressure here, I have a pressure there, I'm not gonna change. When I say maintain the same pressure, regardless of the flow rate I want. Same with elevation. But friction, what's gonna happen in friction if I increase the flow? It increase. Okay. That means I have to understand my requirement from the beginning to cover the worst. Okay? You might be able to design without considering the worst condition. You might be end up then with equipment that will not be able to deliver. Okay? So you have to understand the system resistance. So this is like the first one is the pressure difference. Okay? And pressure again can be converted into head by that formula we went through. Elevation difference. Okay? And the friction resistance. If I have, for example, a cooler, if there is like a control valve, it's not here. Control valve, what's going to happen if I close the control valve? Huh? In terms of friction, more friction. Okay, so I have to consider this in my design to overcome that friction. Okay, and that's a reason to. Another way, I have to understand how much flow requirement that the pump is going to pump. So whenever you change the friction by increasing the flow rate, you will basically increase exponentially the pressure drops. Okay.
What is K? I'm sorry.
It's a factor. Now we're talking about the friction factor. Okay.
And is it based on standard or based on?
No, it's based on the system friction. How much friction in the piping? How much friction in the static equipment and in the valve? Well, it's basically we are saying, whenever you increase the friction, this is gonna be like jumping very high, because the factor can increase as well. So in a real system, we might have point A, point B. We have different elements, control valve, whatever static equipment. If we just have all in one curve, we have the pressure difference plus the elevation difference and the friction resistance. Whenever we change the flow rate, this is gonna change, and this will give us the system resistance. Okay, system resistance with considering like the control valve with a certain opening. The control valve or the valves are playing the main factor in changing the system resistance. Whenever you close, it will shift it. So bump curve, to understand the requirement, we have to understand first the system curve, then how much I need to give for the bump. Bump curve shows the relation between the head versus the flow rate. Okay? Typically, the pump performance, centrifugal pump performance curve follow the same behavior. It's a maximum near to the shutoff, zero flow, and the drop with the increase in flow rate. Okay. If I have it in a curve with the system curve, it's basically the equipment will operate at this point. The intersection between the system curve and the pump performance curve is my operating point. So the pump will be basically operated at this point. Okay. Do I need to operate only in that point? I might be, need to operate at different points, like, selecting the equipment to operate here. Okay. So how can I control it? Can I control the equipment or control the system?
I can either, if I want to control the system, I can put a valve to increase the
Yes.
friction, and I can.
Exactly. Can I control the pump?
Yes, so I can have a control drive, I can change the.
Exactly. Good. That's good. If I have a lower speed, I can just shift the curve lower. The pump performance curve can be shifted lower by reducing the speed, or higher by increasing the speed. Okay? So that's one way to adjust this point. Just like moving it from here to here. For example, just if you imagine I'm shifting it here, so I'm gonna operate to this point. Or maybe higher to operate in another point. But, you know, variable speed are very expensive. You don't go with them unless you need them. So there is always economic evaluation. And sometimes they are not even attractive, depending on the system curve. You know, sometimes the gain that you have, depending on the system curve or slope, the gain is not that much. It will not add you a good value. So I don't want to go into details on it, but it's basically run through like economical evaluation. So for the system, we can throttle, and throttling is just shifting it by increasing the friction to be here. Okay, so this is my a new system. I'm operating at this point. Okay, so I'm meeting my requirement. But what is the disadvantage here?
Lost of money and energy.
How do you lose the energy?
Less reliability.
Less efficiency. Continuous head loss.
You are generating more friction to the system.
Okay. Yeah, generating more friction. Yeah.
We can see the loss you have by if we, for example, change the speed and took the bomb curve and intersected with the original system curve, you will see the difference which you already have the line.
But imagine like you don't have a control on the speed. And you have to live with the system. So basically, what's going to happen, you are operating the equipment here. This original curve without throttling, and okay, this value here of head, this is what we basically you lose for control valve, and head downstream the control valve is this value. So you are operating equipment that generate this head and lose this to get this. So it's like huge losses, and you know that need to be considered. You know, sometimes, huh?
This loss is power.
Yeah, loss energy. يعني زي ما ذكرت في الفريكشن في terms of friction في الكنترول valve. It's gonna be like a throttling for the pressure, and that's a losses for the pressure. So, and this has to be like considered during the design, especially when you talk about high energy equipment. You know, sometimes you يعني بعض الاكوبمنت في الديزاينز يوبريت مثلا خلينا نقول 20,000 plus 1,000 horsepower equipment with some throttling. If you lose like 1,000, 2,000, that's a lot. So you have to يعني consider something else. فكل البارامترز هذه will define if I should go with a variable speed, if I should design the equipment to throttle little, but I need to avoid one thing. إنه whenever I design a system that's from day one is oversized, I should avoid this. If I يعني later on realize إنه عندي oversizing, برضو I can improve it by shifting the impeller diameter, by trimming the impeller. I will be able to shift it here and eliminate or reduce the throttling. So that's like a correction for a problem in design. Okay. Now we'll be talking about the NBSH. NBSH is basically suction pressure minus vapor pressure times 2.31 as specific gravity. How much pressure you have in suction flange minus the vapor pressure times 2.31 as specific gravity. It has to be positive value, otherwise you have a problem with the system. We have NBSH available are required. NBSH available is what's available for the system. How much is available for suction flange, in a suction flange, and you have a required, okay, which is the requirement for the pump, okay. So it's a design criteria. It changes with the change in flow rate, okay. When you increase the flow rate, the requirement حق الامبلر will be higher. You have to overcome يعني cavitation with a good margin. NBSH available should be higher than the required. Okay. Whenever you have it lower, you will have a problem. This is what يعني how we explain it here. Let us just imagine إن عندي suction flange, هذا الامبيلر discharge. This is my margin for the NBSH requirement. Okay. Suction pressure, let us say NBSH is this value. Okay. If I have a drop in pressure that will take me to a point of reaching NBSHR, that will have a cavitation to the equipment. عادة الكافيتيشن امباكت ودمج happen في في الاريا هذه بين الامبلر. It's not in the inlet, it's just in the middle. Why? لأنه إذا كان عندك cavitation, usually when you drop the margin, you start to have cavity bubbles. Okay? Generated through stream. بعض الأوقات تكون generated even before getting through the pump flange. تكون في stream because of low pressure. It can generate here. إذا وصلت إلى مرحلة where the pressure started to pick up or to increase, it will collapse. Will collapse حق البubble generate a high energy that might result in a damage, which is like in terms of, it's gonna be like in terms of bettings or damage to the veins, like what we see here. عندنا هنا وعندنا هنا. ما حدثت في ال beginning of the vein. It's in the center where it started to bubbles start to collapse. Sometimes if you have البubbles هذه still not reaching a pressure that will excite it to collapse, it will start together, stick with the surface, تسوي لي زي vapor cloud, and extend إلى the back side, طيب, and collapse in the other side when it reaches to a higher pressure. And that's why you have a cavitation damage in the back side. Okay, that's another mode of cavitation.
How sensitive are the hydrocarbons in that type of damage mechanism compared to water?
Well, in terms of damage, the damage will happen in both. Now we are talking about the energy that will be, generated in this collapse and its impact on the metal. It's a vapor, like a vapor pressure. I wouldn't think it's it has a huge relation comparing to water
There is
and
water or hydrocarbons, okay.
Okay, performance curve with a change in impeller diameter. If I go with a larger impeller diameter, the head will be generated high, which also means the power, and this is the power curve, will be shifted up. One of the problems that we might have, we go with impeller diameter, larger impeller diameter to meet a new requirement. We do the calculation, think everything is good, we go with impeller diameter, then we discover that we did not check for the change in power, and we run with a problem with the motor. So this is something that in the site during the if we need some modification in the site, we have to look at. Okay. Sometimes you go with bump in a series operation, okay, or in parallel operation. Why we go with in series operation? Yeah.
Increase the head.
To increase the head. Sometimes we go with what we call booster pump and shipper pump. If you remember when we talked about the cavitation, we said the more flow that you have, the more requirement for the NBSH. I mean flow and pressure, the more requirement of NBSH that pump will require. So what they do, Sometimes they improve it with only a booster pump that will just boost the pressure a little bit. Yeah, so the differential pressure of that pump is low. It's just there to boost up the pressure, to improve the suction pressure before you introduce the second pump. The result is you have to understand the behavior of the system by operating these two pumps, because you're no longer comparing only one pump, you are comparing two pumps. Okay, so this is the single pump performance curve, this is the two pumps performance curve. The intersection point is your normal, your operating point now. So you have to consider this curve, not this curve, during the in-series operation. As you can see here, if we are talking about like a double pumps, similar pumps in series, we are having the flow without any change. It will pass through this pump and the other pump. So you're not changing the flow rate, however, you're doubling the flow, the pressure. So for any given flow rate, okay, the pressure will be increased or the head will be doubled. So this is why you end up with this kind of curve, okay? While if we talk about in parallel operation, we are basically looking for a flow, more flow, while the head will be the same. You are not going to double or change the flow, the pressure. So for any given head, you will double the flow rate. So this is why you end up with a stretched curve, not unlike the other one, for a double, parallel operating equipment. And my performance curve is here. Okay.
So when we double the flow, we must watch out for LBSH requirement. If we increase the flow with a parallel operation.
You are looking at it individually. Individually, you'll look at it. Okay, it's a suction condition. Okay, you are not looking for the the NBSH curve for like combined, because you are looking for individual. How much is passing through? It's a suction condition. How much the flow? How much is the NBSH for that equipment?
Okay.
Yes. There is one important thing when we look at parallel operating equipment. Let's see. Whenever we have like a different performance, how is the system response? Actually, the system will operate, or the equipment will operate based on the backup pressure from the system. It will try to give that system whatever pressure it's pressure or head the same. That's needed. So if we have like this pump, it's operating to give this head, and I have a sister pump next to it, but it's not a good condition. It's maybe old, aging, lower performance. What's going to happen in this case?
The flow will go into the pump.
It's not flow. We're talking about head now. The system I have two pumps, it will try to give a head in that location similarly. Okay? How is the pump going to react? It will depend on their performance. If I have, for example, equipment that's already brought back from the maintenance, from the shop with a good maintenance, and this is an old equipment, they will try to give the same head. So let us say this is the head requirement. Okay? That means this pump will be operated at this flow rate, and this pump will be operated at this flow rate. Okay. This is a bad performing equipment, and running it at a very low flow rate, what's going to happen? You will kill it. You will run it in cavitation, you will run it in like a vibration. But sometimes as well, operating this pump at a very high will also gonna kill it. Because you are looking for a trouble zone. Like running it very high, also in an unstable zone, high vibration, and sometimes you will end up with damaging the two equipment. So it's always recommended. We say, if anyone bring the equipment back from the operation to check the performance. Okay, باقي كم سلايد؟ سمحت لله.
خذ راحتك.
There are different ways of controlling the flow. The basic is to control it through control valves. For parallel operating, we have like the control valves, so it will bring the system, control the flow rate to make sure they deliver the same. And there is another way. I mean, there is a different, minimum flow control or recycle minimum flow recycle control. That will prevent the equipment from running at low flow. Okay, what does it do? عندي أنا system requirement. I don't want to pump, like a high or خلينا نقول rated flow. But at the same time, I need to protect the equipment. I can generate like a 50% of the required going to the system and the other recycled back. So this will protect the equipment from running at very low flow, and they prevent it from like having damage because of vibration or running at low flow. So this is one. بعض المرات I need it for switch over between equipment. Okay. Yeah. To control the flow, we use a throttle discharge flow, little control valve. This is or variable speed. طيب. Suction throttling is not used. Why? Cavitation. Yes. So it's always at the discharge side. معنا بعض المرات ترى الاوبريشن
It's not wise.
they play magic sometimes. Yeah. Suction strainer برضو is not recommended because also it's reducing pressure. But guess how? Operation, they love it. They always, and I'm not talking about, it's everywhere.
كمان operation engineer.
Huh? Okay.
كمان operation engineer.
لا لا لا, I'm saying, it's,
It protects the equipment, right?
yeah, you see? لأنه it's okay. Sometimes there is, okay, the pump itself is designed to pass, خلينا نقول certain size of solids. I'm not saying sometimes safety shoes. If it start في التانك, it might be end up yeah, it's, I'm not joking مثلا Aramco or bolts or whatever. So suction strainer, they are used to protect from solids خلينا نقول اللي جاية من البروسيس itself, not the abnormal solids. Okay? Huh?
Like a filter.
Like somehow some process احنا نقول when I say نحن مو أقول لك أرامكو بس everywhere. Yeah. Suction strainer is not recommended unless required by the process. And if you require it, you have to design for the worst condition and to count for like a high differential pressure through the strainer, so the equipment will be sized right. It will not run through cavitation. لكن sometimes حتى الdesigner they don't consider it at all, and when they operate with a like a fine filter, they might be end up with a cavitation issue. So strainer is not recommended unless it's required.
Strainer, as a matter of fact, if you allow me, makes sense to an extent. strainer مش حق السايز is larger than الفلتر. فالبريشر دروب فيه بيكون أقل من الفلتر.
تعتمد.
لكن لو في فلتر هنا question mark.
مو أنت تعتمد برضو على أنت what you are looking for. إذا قلت تقول لي large opening, you are not looking to catch fine dirt. ولا السيفتي شوز هذه. هو شوف في عندنا في النورمال شنو use startup strainer. Submesh, you use it to catch these during the startup. Any leftover things, helping to it will be collected here. Then you remove it. You remove the dirt هذه. Then you remove the strainer. Just only for startup. You are not supposed to receive these during a normal operation. Okay, we are almost there. Common system control centrifugal must be protected against low flow, as we mentioned. Flow, we don't never heat. Why? Because we might run through cavitation. Minimum flow is normally 25 to 30 at the best efficiency. This is how we have, manual flow, recycle back or minimum flow protection. Sometimes it's manually, but mostly it's automatic. Sometimes you have it common at different operating pumps, and sometimes it's individual. Yeah.
There are
يعطيك العافية.
Thank you, Mr. Louay, for a great explanation. Thank you all for coming today. But before we conclude, we need Turkiya Sharani to hand the certificate to Mr. Louay Al-Faiz for her great effort today. Guys, before we conclude, we have to photo with Mr. Louay Al-Faiz. باركود الربع عشان يتسجل لكم في الأنشطة غير الأكاديمية. الله يسلمك.